Hello everyone, welcome to class 6 of Physics 1, where we're going to be doing a continuation of the forces, and we're going to be talking about forces in complex systems. And how we're going to do this is we're going to be applying Newton's second law, mainly in two dimensions, to different types of devices and scenarios. The first one being the Atwood's machine, and then the next thing being the hanging mass on an incline. And with the hanging mass on an incline, we're going to get free systems just by means of using that one formula that's derived from the hanging mass on an incline. And in fact, one of those scenarios that can come from this hanging mass is going to be the Atwood's machine. Now let's talk about our first system being the Atwood's machine. An Atwood's machine is composed of two masses, one bigger mass over here, and then one smaller mass over here, that are connected by a string like this, and then the string is connected to pulleys like this, so the string can freely rotate. And I'm going to define the mass of this bigger mass as capital M and the smaller mass as little m. And what I'm going to be doing is drawing the forces on each of these masses. The first one being the force due to gravity, which is going to be capital Fg, which is going to be equal to capital Mg. So that's the weight of this mass. I'm going to do the same thing for the smaller mass, but this time I use the little m instead for the weight. And then I had this pink arrow here, which represents the tension. And then similarly, there's going to be a tension of the equal value, or equal magnitude that is, on the smaller mass. And I'm going to be defining my direction of acceleration to be downward for this big mass, and then upward for the smaller mass. And in fact, we'll see that the bigger mass is going to be the one that's going to be falling down, while the smaller mass is going to be the one that's going to be going up. So let's use Newton's second law to write the mass times acceleration equations for the big mass and the small mass. So for the big mass, we have big mass, that's big M, times A, that's the acceleration, is equal to our weight over here for the big mass, capital Mg, minus the tension. And why do we do the weight as positive? Well, the weight, the blue vector, is aligned with the red vector being the acceleration. And then the tension is opposite of the direction of the acceleration. And I'll just box that one up. And then we have the small mass, where we're going to be, of course, doing m times a, of course, little m times a, that is. And then our tension this time is going to be aligned with our acceleration direction. So tension is going to be treated as positive. And then we have the weight, which is going to be negative because that's opposite the direction of the acceleration. Now let's start combining things together. And the way we do that is we add the left and right hand sides together, or we add them separately. So let's do this. So we have the left hand side, LHS represents left hand side, and we have capital MA plus little ma, and then I'm going to be factoring out the A, and then just have the sum of the masses in parentheses here. And I'm going to be doing the same thing for the right hand side, RHS that is, and then we get this side here, which is capital Mg minus T, plus the right hand side of our small mass, so I'm taking this plus this. And then once I do that, I can see clearly that the tensions cancel out. and then we end up having capital M minus little m times g. And what we do is we're going to eventually equate this and this together. And that's the next step. So what we have here is we have our left-hand side equal to our right-hand side, and then we rearrange to solve for acceleration of the system, and this is what we attain. So this is going to be the difference of the masses divided by the sum of the masses, all times our gravitational acceleration, g. Now let us do a system that's a little bit more complicated, which is known as the hanging mass system. And what we have here is that there is a mass that is going to be situated on the incline that is connected by a string, where the string rests on a pulley, so the string can rotate once more, just like the Atwood's machine. And then we have a bigger mass, or it could be a smaller mass. I'm just going to denote it as a big M right here, that is going to be hanging like this. And then this incline is going to have an angle of theta. So, what I'm going to be doing is I'm going to be putting some forces on each of these masses. And we can see clearly that, like, if we take a look at, say, maybe this capital M mass over here that's hanging, we can see that there's a tension due to the string that is going upward. And then we have a gravitational force, which is going to be downward, because, well, gravitational force is always pointing towards the center of the Earth. But if we take a look over here, things become a little bit more complicated. So, on our masses on the incline, we have our gravitational force for this mass being downward, and that makes sense, because gravity is towards the center of the Earth. And then we have our tension, but this time the tension is going to be going along the direction parallel to the incline. And then you have your normal force, which is going to be perpendicular to the incline. And then you have your friction, Fk, which is going to be parallel to the direction incline, except going in the opposite direction of the tension, assuming that this mass, little m, is going to be moving up the incline, that is. And under the assumption that we're going to be moving up the incline, I'm going to say that positive x is going to represent that direction for this little m mass here, and then positive x for this capital M mass here. And just one other thing to mention, since we know the angle is theta right here, we can know that the angle is going to be theta between this dotted line right here and the gravitational force right here. Now, if I look at the mass on the incline, we can do an interesting trick here with our free body diagram, where I can actually rotate this free body diagram right here to this over here, such that the tension is going to be pointing to the right, and all the other forces rotate as well. And in fact, all these forces have been rotated theta degrees clockwise. So tension's kind of obvious in a way. The gravitational force as well has rotated theta degrees. Friction and normal force as well have rotated theta degrees. And why we do this? The reason we do this is such that the tension, normal force, and the frictional force are all only in one particular direction. And that kind of simplifies our problem a bit, because that means we'll only have to break our gravitational force right here into different components that are composed of x and y components. And if you take a look over here, right, you'd see that you have kind of the inverse situation if you were to consider doing the forces as shown on this diagram. Like, for instance, you see that the gravitational force is downward here. So that's one direction. But then you see that the normal force, the tension, and then also the frictional force would all have to be broken up into different components, which is a much harder problem to deal with. So that's why we like to consider our free body diagram like this when we're dealing with this hanging mass system problem. And then for the hanging mass, this is much simpler. Here we have the tension aligned opposite the direction of positive x. And then we have our gravitational force aligned with the direction of positive x. And essentially, this is just more or less kind of the same situation as what we saw with the elevator problem, except that we're dealing with a tension instead of a normal force. So now that we have our free body diagrams for our hanging mass system, for both the hanging mass and also the mass on the incline, we are now ready to solve a set of simultaneous forces so that way we can calculate an equation for the acceleration, and also other parameters like, say, the coefficient of friction and then also the tension. So I have my free body diagram for the mass on the incline transferred over to this slide as reference. And then I also have my free body diagram over here for the hanging mass transferred over here as well. And my goal is I want to be able to set up some equations that represent the forces in the x direction and then also in the positive y direction as well. So let's start with the x direction. So if I look over here on my diagram, I can see that there are some forces that are going to be in the x direction, including, say, the tension. And then you also have the force due to friction. And then you also have the component that is going to be aligned with the x-axis, which is going to be shown by this laser right here, which is opposite of the angle theta, so that's going to be mg sine of theta. So putting all those forces together, we're going to get tension minus our frictional force, and our frictional force, right, remember, you can write frictional force as mu times n, that is, and then minus mg sine of theta, because, well, the component of mg that is going to be parallel to the x-axis is going to be mg sine. And then you also have the y component as well, which is going to be, you got your n, which is going to be upward, so we're going to treat n as positive, and then we're going to be doing the component of the gravity that is going to be aligned with the y-axis, which is shown right here by this laser. And then you get mg cosine for that component, which is going to be aligned with the y-axis. So then you get n minus mg cosine. And since the box is not going to be moving in the y direction at all, it's not going to be accelerating in the y direction, we can set the sum of the forces in the y direction to be equal to 0. And thus we get our normal force is equal to mg cosine of theta when we solve for the normal force from this equation. And then if we move over to our hanging mass, we can clearly see that this becomes more or less similar to the elevator problem, where we have mg minus tension is going to be equal to ma. mg because it's aligned to the x-axis, and t is going to be negative because that's anti-aligned with the positive x-axis. And that's all equal to ma by Newton's second law. Now, what we're going to be doing is we're going to be taking our two equations from our mass on our incline, and then our one equation over here from our hanging mass, and going to be combining them together. And what I'm going to be doing to begin this is I'm going to be combining the forces in the x direction. So I'm going to be adding this force here, the force in the x direction for little m, and the force in the x direction for capital M. And when I do that, adding the left and right hand sides together, just like we saw at the Atwood's machine, I could see that the tensions cancel. So the tension here and the tension here cancel. So cross that one out, cross this one out, and then we're left with capital Mg, and then we have this term here for the friction, and then this term here for our gravitational component. And then when you mesh all that information together, you get capital Mg minus your frictional force minus your mg sine theta as your left-hand side. And then you do the right-hand side, which is going to be capital Ma plus little ma, and that will give you the sum of the masses times the acceleration. And then what you could do is rearrange and just solve for acceleration, which is pretty much just dividing by the sum of the masses. And then you get this equation right here. But why just stop at the acceleration? We can solve for more things, including the tension and the coefficient of friction. So what we could do to solve for the tension, right, is we can get T is equal to capital M times G minus A, which is just pretty much directly from your hanging mass equation over here. So just rearranging, solving for tension, that's what you get. And then what you could do is you can stick in this expression for A up here into this equation right here, and if you do the algebra and simplify it down, you would get this expression right over here. And then you could also solve for the coefficient of friction, which is just pretty much derived from up here, where you have this equation right here. You have T minus your frictional force minus mg sine theta is equal to ma, and that is going to be rearranged to solve for your coefficient of friction, while also considering that n is equal to mg cosine of theta. So if you were to rearrange, do the algebra out, you get this expression right here. And then I'm also going to be sticking in this expression here for the tension as well. So sticking in the tension, we get this entire equation right over here. And then I can simplify this equation, and then I get my coefficient of friction as being this equation right here. Now, we went through quite a bit of rigorous work for us to be able to determine the acceleration for our hanging mass system, but interestingly enough, you can actually use that one acceleration equation from the previous slide to generate three systems. And I'll show you what those systems are going to be. So, we have our general equation right here for acceleration, and we have our first system that we dealt with earlier today, which is going to be the Atwood's machine. But if you really think about it, right, the Atwood's machine is technically a hanging mass system with the angle theta set to 90 degrees. And also, there's no friction involved because there's no contact with the surface. So what we do is we can set our coefficient of friction equal to 0, and then we also set our angle equal to 90 degrees. And that will affect only the inside terms right here. So what we have here is, since you have mu is equal to 0, that means that this term is not going to matter. But then since you have sine of 90 degrees, that is going to turn to 1. So your equation is going to reduce down to capital Mg minus little mg over the sum of the masses, which in turn turns out to be your Atwood's machine acceleration equation. But why just stop at the Atwood's machine? There's more. You could also consider the case where there's no friction at all. So what we do is pretty much just turn off friction by setting mu k is equal to 0. And then with that, our acceleration reduces down to this equation here. So that's just pretty much just vanishing this term right here. We get rid of mu k cosine of theta. And then there's also one more, but this one I'm going to leave as an exercise because you're going to be doing this in the activity. It is going to be hanging mass with a flat surface. And what you do with this is you can set theta is equal to 0 degrees. So apply pretty much more or less the same logic we saw with the Atwood's machine, and then the incline with no friction to your general equation right here, and identify special conditions, like say you got theta is equal to 0 degrees. Apply that to this equation. And then also you might have friction, right? You have the frictional force this time, not the coefficient of friction in your activity. So I'll leave it as an exercise for you to figure out what to do in order to reduce this equation down into an appropriate form that describes this system right here.